Assalamu alaikum everyone. So lecture number 24, and we will be having review and recap of the chapter that we have finished during last lecture, and we will be following the same format. First of all, we will have the review question, and then we will try to quickly cover the topic that is relevant to the underlying review question. So let's start. So these are the bullets which we will be going through one by one. Parity. So how the parity is used in order to accommodate the error detection, and then CRC, that is cyclic redundancy check, another error detection scheme. Then how the CRC have the capability, because the problem with parity is that there are certain limitations. For example, if we are using 1-bit parity, then we cannot detect errors if there are 2 bits that have been affected by the error. Then we need to go for some other error detection scheme. So how CRC make it possible to detect more than a bit error? Then when we talk about CRC, it has different algorithms. So we will be having a review question from the CRC algorithms, and we will be going through those different algorithms fastly. And then ECC, error correcting codes, and we have two different type of codes, and we will be talking about block codes and convolutional codes. So first of all, the question is, review question is, what is a parity bit, right? So as we first have to detect error, and then there are certain codes that have the capability of error correction. Okay, and error detection is something else, and its correction is another sort of algorithm. So some error detection, some encoding schemes, they support error detection and error correction, but some other schemes, they only support, or they can only detect errors. So in order to correct errors, in that case, we have to go for some other algorithm. So here we have different error detection methods, and these are parity check. We can have CRC, again a detection method, and then we have another method, that is the checksum, right? So here let's talk about the parity check. So for example, we have a certain number of bits, and we want to ensure that the error has to be detected in case if there is some error when we transfer data from one point to another point, or from transmitter to the receiver. So even in within the computer, for example, we take the example of a motherboard. So there are different parts on the motherboard. There is memory, and there is cache, and there is processor, and there are some other units that are exchanging data frequently. So in that case, from one unit to another unit, we can also use parity. This is so in between there are certain layers of copper. So we have multi-layer PCB, and those different units, they are actually being joined together by using the copper that is acting as a channel. So in that case, we can also use parity. For example, we have to transmit data from the logic unit to processor. So in that case, we can also use parity, and in that case, our transmitter is logic unit and our receiver is the processor, and in between we have the copper wire on the PCB that is acting as a channel. So we can also use parity at different stages and different scenarios. For example, we can also use parity when we have to transmit data from one computer to another computer by using UTP, unshielded twisted pair, or maybe coaxial cable, or it can be shielded twisted pair. So it depends on the scenario. So what scenario we actually are in, and our requirements, right? So maybe the parity is best solution for some scenario, and it can be a worse solution in some other scenario depending upon the requirements and objectives. So what normally we do when we use parity as error detection is add it to every data unit. For example, we have a data unit of 4-bit, right, and we have to add a redundant bit, that is the parity bit. Total number of ones including the parity bit becomes even. So we have two different types of parity, even and odd. So the total number of ones should be even if we are using even parity, or odd if we are using odd parity. So here we have the receiver node and accept data, right, and here we have the sender node, right. So this is the data, original data. So you can see 1, 2, 3, 4, 5, 6, 7 bits are the data unit, and we are actually calculating parity by using this block, and this is the redundant bit, right. So you can see that over here we can count the number of ones. So they are odd, 1, 2, this is 1, and here we have the second, and here we have the third. So we have 3 ones, and in order to make it even, because we are using even parity over here. So in order to make it even, we have to add this redundant bit. So this is actually the redundant bit. Okay, so and so as I have mentioned, so we can assume that this is the sender and this is the receiver. So this is one unit within motherboard, and this is another unit onto the motherboard of the computer. So for example, this is the logic unit where the logical operations has to be performed, and here we have the processor. Maybe you can say that this data is sent to the processor for some sort of verification or for some sort of output. So this data has to be sent to here, or you can also take another unit in different scenario. So in between, this is the transmission medium. So this can be a copper wire, right, and this can be a fiber optics if we have to transmit data by using light signal, and there are number of scenarios we can take into account, right. So I have mentioned most of the scenarios by taking this parity check as a error detection scheme. So transmission medium, right, channel, and then the bits have been received, and here we will performing the check. This is the parity, here parity generator, and here parity check. So if here we have to decide either data is correct or incorrect. So as mentioned, this parity check will not detect error if we have error in 2 bits. Let's take the example. With the same data, we have 1, 1, and then 4, 0, 1. So, and remember that this is the redundant bit. So let me put a box around this redundant bit. So 1, 2, 3, 4, and we are actually having even number of ones. So in normal conditions, if this data is received correctly, then this parity check will, including this one, will count the number of ones, and if it is even, so it means data is correct and has been accepted, otherwise it has been rejected, and the receiver will send a request. So processor, in case of a computer, processor will send a request to the logical unit to resend the data, right. So there can be a scenario, for example, 1, 1, and let me put 0 here, 1 here, 0 here, and 1 here, and then 1. 1, 2, 3, 4, 5, 6, 7 bits, and you can see now let's compare the corresponding bits. This is correct, this is correct, this is also correct, and here there is some problem. So let me put a cross over here, and this is again correct, this bit, and again here we have a problem. So we have problem here, and again there is no problem over here. So we have compared the corresponding bits, and even we have error. So you can see, we can count. So this is the redundant bit, 1 2 3 4 5 6. So now even we have error, this parity checker circuit will say that the data is correct because we have error in 2 bits. So this is the bottleneck, and this is the limitation of the underlying error detection scheme, that it cannot detect error when we have error in 2 bits, and that can be the case when we are transmitting data from one point to another point, from one unit to another unit. Okay, known as single error detecting code. So that's what we have discussed. SED, only useful is if probability. So remember, we can calculate the probability of error if this is the case within our system. So this parity check method will work if the probability of getting 2 errors simultaneously in a single data unit is very, very low, right? So the recommendation is that we should use this parity detection methodology when the probability of getting errors in a single block, in a single data unit within 2 bits, right? Or let me rephrase it. So we should use this parity detection scheme in a single data unit where the probability of getting simultaneously 2-bit errors or errors in 2 bits is very, very low. The probability should be very, very low, or the probability of getting 2 errors should be very, very low. So normally we prefer this methodology in serial communication, okay, and because the number of bits which have been added as a result of this error detection mechanism, so it's on the lower side, only one bit is added. So of course if we have to add more bits, so we have to transmit more number of bits alongside the data unit, so that will make the circuitry complicated, and then we need more bandwidth in order to transmit those bits. So it introduces low overhead, but on the other side it is not very powerful, as mentioned, that when we have errors in 2 bits simultaneously, then it will not work. The coder can be implemented efficiently using a tree of XOR gates. So we can use XOR gates. So we will be discussing the circuitry after a couple of slides. So here we have generally explains or mathematically represent the parity codes. So example of a simple block code. So it's actually a block code because we normally take the blocks, that is a single data unit, and then we add the redundant bit, and then we take the next block. So it's actually a simple block code, so you can name it as a block code. So here n is equal to k plus 1, that is the code word is the data word with 1 additional bit. So k plus 1, this one is the redundant bit, so the code length will become k plus 1. For even parity, the additional bit is, right, so you can see I is equal to 1 plus k di modulo 2, and for odd parity, bit is 1 minus q, right. So additional bit ensures that there can an even or odd number of ones. So this is the mathematical representation of the parity code. So here we have mentioned different examples. even parity. So this is the data, original data. So after coding, block coding using parity, we have introduced this one. This is the extra one. That box should be there, right? So you can see number of ones are odd, and we are using even parity. So to make it even, we will add this redundant bit 1, 2, 3, 4. Let me mention over here. So 1, 2, 3, and 4. So we have 4 number of ones. So as even parity, and this is the redundant bit, right? So we are using even parity, and here we have the data 1, 2, 3, 4. So the number of ones are already even, so we will be placing 0 at the parity bit position. 1, 2, 3, 4. So we put arrows over here, so 4 ones. Okay, so here we have mentioned the table. So what we can have, we can use the table straight away. So the length of the data word is 3, and we have, after the addition of the parity bit, we have the code word, and you can see the number of bits are now k plus 1. So here k is equal to 3, and this is the length of the code word, n is equal to k plus 1. So it's 3 plus 1 is 4. Right, so that's why we have mentioned coding table for 4, 3 even parity code, right? So 0, 0, 0, and remember that this slot is actually parity bit slot, right? So let me mention in this way, right? So this is the actually parity bit slot. So you can see number of ones, right? So 0, right? So there is a debate. There can be a debate that either when we have number of ones 0, so it can be even or odd. But here you can see 0, right? Then 0, 0, 1, 0, 0, 1. So in order to make it even, or 2 number of ones, 1, 1. So you can see again 1, because number of ones are odd here, even number of ones here. So let me write down. So even, we have taken this even, odd, odd, and even, right? It should be odd. Okay, and here we have even, and odd. So I can straight away put the 0 here. So this is odd, 1 here, this is odd, 1 here, and even 0 here, odd, 1 here, in order to make the odd as even, 0, even 0, and odd 0, right? So here. So now let's come to decoding, right? So calculate sum of received bits in block. So remember that here we are in modulo 2. Sum is 0, 1 for even odd parity. Sum is 0, so it means even. If sum is 1, that means odd. Parity, then the data word is the first k bit of the received, right? So as mentioned, we have mentioned n is equal to k plus 1. So this first k bits of the received code word, this is the actual data. So otherwise error, code can detect single error. This is the bottleneck, cannot correct errors. So this again, this code don't have the capability to correct errors in any bit, right? So for example, if we have 1, 0, 1, 1, and we are using even parity, so of course here we have k is equal to 4, so n should be k plus 1 is equal to 5. So let me place, so this is the parity bit, and we have made we are using even parity. So the system should be knowing. So if there are some errors, so 0 and 0 1 1, right? So though we have detected the error, right? So here we will be having 0. So this is the sender, and here we have at the receiver we have 0. So though the receiver identified the error, but it cannot identify the position of the error, right? So you can see that here the error is in, if we look at the most significant bit, so the error is on the most significant bit side, right? So that's is what has been said over here. The transmitted data word could have been, right, or with the error being in the first or the second place respectively. Error could also lie in other positions. So this is the bottleneck, that this code don't have the capability to detect the position of the error, right? Okay. Simple parity: if performing even parity, add a parity bit such that an even number of, so it's the same example is almost the same, and here character is sent and first two zeros accidentally become two ones. So of course this is the bottleneck, parity error. So here we have longitudinal parity. So we can define another algorithm in order to detect more than one errors. So that's why we are going to define longitudinal parity. To each character then sends a row of parity bits after a block of characters. Right? This row of parity bit is actually a parity bit for each column of character. The row of parity bits plus the column parity bit add a great amount of redundancy to a block of characters. So here you can see we have row 1, right? So now we are dealing with the data in rows. So this is the parity, right? So you can see parity 1 2 3 4 5. So we are using even parity over here. So let me write down over here even parity, and the number of ones one, 2, 3, 4, 5. Number of ones are odd, so in order to make it even, we have to place a 1 here. So similarly 1, 2, 3, 4, 5, 6, 7. So 1 to make it 8, that is even. And here 1, 2, 3, so odd. In order to make it even, we have to place 1 here. So now this is the parity when we talk about the row. Now let's talk about the column. So we are actually going to add more redundancy in the data. So these are the column positions, right? So you can see this is the parity row, not the actual data. So 1, 2, 3, and you can see we have placed a 1 here in order to make the number of ones even. So 1, 2, 3 odd, and we have placed a 1 here in order to make it even, right? So similar is the case over here, and here we have 1, 2, 3, 4. Already number of ones are even, so 0. Number of ones are even, so 0. 1, 2, 3. Number of ones are odd, so in order to make it even, 1. And so this is the parity row. So we can again calculate the parity for this parity row, 1, 2, 3, 4. So you can see a 0 over here. So what is the advantage of this? So now you can see that we have to send more data, right? So actually if we are going to send this data 1, 2, 3, 4, so we are actually sending this redundant data, and this row, whole row, and this is again the redundant data, and the actual data is row 1, row 2, row 3 and row 4. So what should be the benefit of adding this more number of bits? So you can see the second and the third bit in rows 1 and 2 have errors, but longitudinal parity does not detect error. Okay, so you can see the longitudinal parity are not detecting errors. So 1, 2, 3, 4, 5. So again, this is 1. So in the previous slide you can see 1 here, and 1, 2, 3, 4, 5, again 1 here. But if we look at the data, this is 1, 0, and here we have 0, 1, and here we have 1, 1, and here we have 0, 0. So they are error in 2 bits, but the longitudinal parity is not capable of detecting it. So now what we can do, so we can see that 1, right, and do not catch all errors, right? So simple parity only catches odd number of bits error. Longitudinal parity is better at catching errors, but requires too many check bits added to a block of data. We need a better error detection method, right? So here we have another example, right? Here sender wants to send the word in ASCII, right? The 5 characters are coded, so these are the 5 characters, WORLD, word, and here we have the code after adding the parity, and now you can see is received by receiver without being corrupted in transmission, right? The receiver counts the number of ones each character and comes up with even numbers. 6, 6, 4, 4, 4, the data are accepted, right? So here we have the example. So here we have error, you can see 6, 6, 4, 4, 4, 7, 6, 5, 4, 4. So data is corrupted over here, right? So here we will be explaining what are the benefits of having extra bits over here. So here we have the explanation. Original data, right? And this is the row pattern, and here we have the column pattern, right? So 1, 1, 0, 0, 1, 1, right? So this is the parity, and here we have the data and parity bits, right? So 1, 1, 0, 0, and this is the parity, and here, right? And here we have the column parity, right? Suppose the following block is sent, if it is hit by burst noise, right? So you can see that we have the burst noise over here, right? And this, as a result, those two data units will be discarded, and if the sender and receiver, they have the capability, so the receiver can send the request to resend those data blocks. Checks the parity bit. Some of the bits do not follow the even parity rule and discard it, so it will discard the whole parity. So here we have mentioned the table for even and odd parity. So if we have the same number of data unit, and we are going to mention the odd parity and even parity over here. So even, right? So odd parity. So in that case, even, odd. So we can have. So here we have another example. Is set to transmit a file using 8 data bit followed by 1 parity bit. So 1 byte plus 1 redundant bit. The port is set for even parity. Receiver. So another computer receives the following 9 bits string, which is valid and which contain an error. So the computer, or the sender and the receiver, which are actually computers, they have to find out that which data is correct or valid and which data contains some error. So here even, number of ones, no error. So here you can see odd, number of ones, so error, 2, 3, 4, 5, 6, 7, 8, 9, right? So here again, number of ones are even, so no error. So here we have the parity generator circuit. So for example, 7-bit ASCII code. So we have taken the example previously that where we have to send. So each alphabet is represented by a 7-bit ASCII code. So character contains an even number of ones, this output will be 0, and odd number of ones, this output will be 1. So parity generator circuit is composed of XOR gates, and they are connected together in such a way that they can generate even and odd parity as well. So here we have mentioned the data. So first start bit, and then we have a stop bit. You can see over here this is start bit and this is the stop bit. So the data is 1 0 1 1 0 0 1. So this is the parity generator circuit. So we are going to use this circuit in order to generate the parity. So let me mention over here. So 1, we place here 1, and here we have 0, then here we have 1 1, right, and then next we have 0 0 over here, and here we have 1. So this is the truth table for XOR, and you can see when we have both the inputs same, we will get 0 0 0 1 1 0, and if either one or one of the input is high, so it will give us a 1, right. So here you can see that if this is the data bit and this is the parity, so you can see that it is actually favoring the irrespective of those combinations, so even and even. Okay, so now we are going to use this truth table in order to have our result. So 1 0, we will be having 1 over here, and 1 1, both the inputs are same, so 0, and 0 0, we are having 0, and then 1 here, right. So this one is here, so 1 0 1 1 1 0 0 0 0, and this is, so now we can have value for this 1 0 1 1 and 1 1. So this 1 1 is here, and so you can count the number of ones, 1 2 3 4, right. So it means if I write like this, 1 0 1 1 0 0 1 1 2 3 4, and we have, so if we are going to use odd parity, so that will be, so this 0 will be inverted and will be having, so this is parity bit that is generated by this parity generator circuit, and this is the even parity. And if we are going to use odd parity, right, so we will take the output after inversion, and you can see we will be placing a 1 over here, 1 2 3 4 5, so this is odd parity, right. So now let's have a look at the parity checker circuit. Okay, so the data is same, and now we are going to draw the parity So you can see that I'm using XOR gates again in order to have the parity checker circuit. Right, so these are the inputs. So 1, 2, 3, 4, 5, 6, and what I have to do, I have to go for 7, and here I have, so 1, 2, 3, 4, 5, 6, 7, 8. So the data is 1, 2, 3, 4, 5, 6, 7, 7-bit data. So this is the actually data unit. And after having 1-bit parity over here, so 1 0 1 1 0 0 1, and I have the parity bit slot over here. So these are, this become 1 2 3 4 5 6 7 8, right? So here if I have to mention k is equal to 7 and n will be k plus 1, that is 8. So that's why I have 8 lines. This is you can see if I start from the most significant bit, and this is the least significant bit over here, right? So this, let me mention parity be even, because we are using even parity. So let's put like this 1 0 and then 1 1 0 0 1, and this is the parity that has been generated, that was 0 because we are using odd parity. So 1 0 1, so 1 1 0, so let me place 0 over here. So 0 1 1, so 1 0 again 1 here, and 1 0 1 here, 1 1 0 here, and 0 0 0 here. So if 1 0 1 1 0 0 1, and this is the parity, so I have to count the number of ones, 1 2 3 4, so including the parity. So this is important, that we have to add the parity bit when we are counting the 1, right? So there can be a case, for example 1 0 1 and 1 0 0 0, 1 2 3 4 5 6 7, and we have to place 1 here. So now when we are counting the number of ones, so we have to add the parity bit 1 2 3 4, right? So now this parity checker should have a 0 here when we will be using this as input. But here we have, you can see we have included the parity bit, so we are actually calculating the number of ones in this 8-bit data unit that includes 7-bit actual data and 1-bit parity, right? So you can see 0, this is the parity bit, number of ones are 1 2 3 4, so already even, and we have the, so there can be a scenario, for example, if I place 0 here and I place 1 here, right? So actual situation is that here we have 1 and here we have 0, so I have inverted them. So now we can see the, so that again this checker will be saying that data is correct, but actually it is not correct. So 1 0 1 0 1 1 1 0 0 0. So let me put here, right? 0, because 0 0 0 0 1 1, this 0 and this 1, and then 1 0 1 and 1 1 0 and 0 0 0. So you can see, because we have error in 2 bits, so even this parity checker, so this is the parity checker circuit. So in that case, even the parity checker circuit don't have the capability to detect errors when we have error in 2 bits simultaneously. So now after discussion, we are in a position to answer our question a parity bit appended to an array of binary digits to make the sum of all binary digits including the parity bit always odd parity, or always even parity, right? So we have to count the number of ones. So now we have a review question from CRC. What is cyclic redundancy check? So here again I've mentioned detection methods. So you can see detection methods. We have parity check, CRC, and checksum. So redundancy, so you can see that data, original data, and then we have the generating function and redundancy check, and this is the sender, and on the receiver side we have the checker, accept, or, so we have to decide either to accept data or to reject data. So this is the addition of redundancy, right? So this is the data and this is the redundant data or redundant bit. So we have 4 different types of redundancy checks that are being used in data communication. So we have VRC, LRC, CRC, and checksum. So let's talk about VRC, right? So this is the data, right? And we are actually using parity over here. So that is the vertical redundancy, right? So you can see we have data, and this is the extra bit that has been added. So checking function, number of ones are even. So this parity generation and then parity checking is called, or parity encoding is called VRC, that is vertical redundancy check. And let's talk about the performance. It can detect, so because performance is very important for us when we talk about the data communication, so it can detect single bit error. So for me this is useful when we have to send data from one unit to another unit within the computer. So even in that case there are chances that there can be some errors in 2 bits. So we can use some other methods in order to detect those errors, and then after detection we have to take corrective actions in order to retrieve the data correctly, right? So this is the bottleneck for this VRC. Can detect single bit error. It can detect burst errors only if the total number of errors is odd, right? So this is the additional point that we have learned. And then we can have longitudinal redundancy check, LRC. So you can see that we have the LRC, longitudinal redundancy check, and this is the extra bits that we have added alongside this data. So this is the movement of the direction of the data. So we immediately jumped onto the performance. So let's talk about the performance of LRC. Increases the likelihood of detecting burst errors. So you can see from, it has the capability to detect burst errors in one data unit are damaged and 2 bits in exactly the same position in another data unit are also damaged. The LRC checker will not detect an error, right? So this is the bottleneck. So you can see here we have combined VRC and LRC, right? So you can see this is the VRC, right? So we have added bits, these are the parity bits, right, for the corresponding data unit, right? So 1, 2, 3, number of ones are even over here, 1, 1, 2, 3, even, and 1, 2, 3, 4 already even, so 0, right? So 1, 2, 3, 4, and 5, 1. So you can see that we have we are using VRC by placing parity bits, and then we have to introduce LRC. So this whole can be considered as, because these all are parity bits. If I go back, so this is LRC, right? So if I place this data in such a way, right, so this will be LRC and this is the data bit transfer of each unit. So this is the direction of transfer of the whole block, right? And then we have CRC, cyclic redundancy check, given a k-bit frame or message. So here we will be dealing with frames, or the transmitter generates an n-bit sequence known as a frame check sequence, FCS, frame check sequence, because we are dealing with frames, so that the resulting frame consisting of k plus n bits is exactly divisible by some predetermined number. The receiver then divides the incoming frame by the same number, and if there is no remainder, assumes that there was no error. So this is a very interesting mathematics that is involved. So if we talk about the TCP/IP stack, so on the MAC layer, right, or on the data link layer, so we are actually dealing with frames. So then we can assume that this CRC has to be working there. So here we have the binary division, and this is divisor, quotient, and remainder, right? So this is the actual data, and then we have divisor, and this is the quotient, and you can see this is the remainder. We can also use polynomial in order to generalize or generalized representation of the underlying CRC, x7, x5, x2. So you can see we are 1, 2, 3, 4, 5, 6, right? So it's polynomial. So here we have, you can see the x7, x5, the bits that have 1 at their corresponding positions. So we will be writing on the polynomial in such a way, x7. First you can see that we have 0, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, right? So we are actually counting starting from 0, right? So you can see x5, right? So this is 5, and here we have 2, this is 1, and this is 0, right? So divisor, and we have different standard polynomials, CRC12. So you can see that this is goes up to 12, 0 to 12, right? And CRC16 and CRC-ITU and CRC32, right? So checksum, this is another mechanism that is used for the underlying error detection scheme. So you can see that the checksum, we have section K, and we have divided into different sections and the corresponding number of bits, right? Section 1 n bits, section 2 n bits. So each section has n number of bits, right? So then we have sum and complement. This is checksum, sender, and then on the receiver side, all ones except otherwise reject, right? Sum, checksum, and unit is divided into k sections, each of n bits. All sections are added together using ones. Complement to get the sum is complemented and becomes the checksum. Okay. At the receiver, k sections, each of n bits, all sections are added together using ones complement, right? So the sum is complemented, the result is 0, data are accepted, otherwise they are rejected. So it involves more DLD, digital logic design. So you need to know the complement, ones complement, and twos complement, right? So here ones complement, sum is complemented. Checksum detect all errors involving an odd number of bits. It detects more errors involving an even number of bits. If one or more bits of a segment are damaged and the corresponding bits of opposite value in a second segment are also damaged, some of those columns will not change and the receiver will not detect the problem. So this is the bottleneck. So of course, after detecting the error, there should be some error correction mechanism. It can be handled in two ways. Receiver can have the sender retransmit the entire data unit. So this is one possibility. Can use an error correcting code. So we can have another algorithm in order to correct errors, and that automatically correct certain errors. So here we have single bit error correction. To correct an error, the receiver reverses the value of the altered bit. To do so, it must know which bit is in error. So we need to know the position of the error in a data unit. So in order to use this single bit error correction scheme, the receiver must know the position of the bit that actually are introducing error. Bits needed: let data bits M, redundancy bit R, so total message sent M plus R. Following relationship, 2 raised to power R is greater or equal to M plus R plus 1. So error corrections, so you can see data bits and these are the redundant bits, and we have total M plus R bits. So we can use Hamming code, right? So you can see that these are the data bits, and then we have redundant bits that are introduced in between the data bits, right? So here redundancy bit, so these are the redundancy bit, right? So Hamming code, you can see R1 will take care of these bits, right? So this R1, R2 will take care of these bits. Those are mentioned: 2, 3, 6, 7, and 10, and 11, right? So you can see that these are actually mentioning 8 plus 1, 9, and then 8 plus 2 plus 1, 11, right? So R4 will take care of these bits, and so forth. So here we have the example of Hamming code, right? So single bit error, so error detection. So these are the steps that actually are involved when we talk about the Hamming distance calculation. Strings are of equal length. So this is you can say the necessary condition in order to have Hamming distance calculation. Can only be calculated between two strings of equal length, right? String 1 and string 2. So you can see they should be of equal length. First two bits in each string, if they are the same, record a 0 for that bit. If they are different, record a 1, right? So it's a sort of XOR for that bit. In this case, the first bit of 4 strings, both strings is 1. So record a 0 for the first bit. Compare each bit in succession and record either 1 or 0 as appropriate accordingly, right? String 2, so we have recorded this. Step 4, add all the 1s and 0s in the record together to obtain the Hamming distance. So Hamming distance is 6. So if we are using a computer, so we can apply XOR, can be used to compute the 2 strings, and then we can obtain the record. So now we are in a position, or we now can answer our question, that is, what is CRC, error detecting code, in which the code is the remainder resulting from dividing the bits to be checked by a predetermined binary number. Right, so here we have to compare CRC and the parity, cyclic redundancy check, and the parity is actually VRC, error detecting code, in which the code is the remainder resulting from dividing the bit to be checked by a predetermined, has more bits, right? So this is the very precise comparison, and therefore provides more redundancy, right? So of course that is, it provides more information that can be used to detect error. So as in case of parity, we are using only one redundant bit, so it is of course carrying very little information in order to detect errors. On the other side, when we talk about the CRC, so it introduced more redundant bits, so of course it will be carrying more information alongside the code, so we are in a better position in order to detect errors. So this is the comparison. So now we have to mention the ways in which CRC algorithm can be described. So Let's talk about CRC. Burst error will most likely go undetected. So whenever we talk about the burst errors, right? So for example, we are sending data, and as we have more bit rate, right? And actually we are sending more bits in a signal. So the baud rate is less and the bit rate is on the higher side. So in that case, there are more chances that in case of there is some problem with the signal, so the more number of bits has to be corrupted. So then in that scenario we can have burst errors most likely, and they normally when we are using simple error detecting codes, so they go undetected by simple parity check scheme. For example, elaborate technique called CRC, so as has to be implemented redundant bits to the frame, right, called frame checksum check sequence at our receiver side in order to detect errors, right? So k number of original data n minus k number of bits in the, so here you can see this is the data and this is total is n. So let me mention over here n, and this is k, this is actual data. So this is the redundant bits, so and that is actually equal to n minus k. So the length of those redundant bits is actually n minus k. So the total number of bits is n, right? So you can, if we solve this, k plus n minus k, so n. So how we generate CRC is all about finding the frame, right, check sequence given data and a divisor p. So this is data, and then we have to generate the divisor p, and you can see that this is the data and this is the divider 1 1 0 1 0 0. So there are three equivalent ways to generate the CRC code. We can use modulo 2 arithmetic method, and we can also use polynomial method, and we can also have digital logic method. So there are three different methods. So here we have modulo 2 arithmetic without carry, right? So equivalent to XOR operation, that is 1, right, 0 and 1 1 1 1 0. So you can, if I write down the, this is the output and this is the, so 0 0 0 0 1 1 1 0 1 and 1 1 0. So this is the truth table for XOR, right? So let me mention truth table for XOR. So you can see that here if I look at the truth table, right, and I have to mention, so 0 0 0 1 0 1 0 1 1, right, 1 1 0, and then if I have to multiply 0 0 1, right? So you can see the examples, different examples, right? So here we have mentioned the error detection process when we talk about CRC. So you can see that given k bit data, right, and transmitter generates n minus k bit frame checksum field f such that the total n bit frame is exactly divisible by sum n minus k plus 1 bit, predetermined divisor p, a zero remainder. Receiver frame may or may not be equal in value and the to the send frame. Receive frame be t, and error-free transmission, and that is t bar. So it's t bar. Receiver then divides t bar by the same known divisor p and check if there is a remainder. If division yields a remainder, then of course there is some error, and if the division gives 0 remainder, then the frame is error free and we will accept the data, unless there are large number of bits in T bar resulted in a new exact division by P, and that is very unlikely to happen, right? So CRC generation, T is equal to 2 raised to the power n minus k into D plus F, right? So here we have mentioned the divisor. Okay, so here we have some sort of mathematical representation, right? So you can see T is equal to 2 raised to the power n minus k into D plus F. F is remainder obtained from dividing by divisor P. So this is the mathematical expression, right? So 2 raised to the power n minus k data, this is P, that is the divisor, and this is the quotient plus F over, this is the remainder, and here we have the divisor. Quotient and F is the remainder, correct, right? So now we are going to introduce certain math, right? So subtracting for the first term from, right? So you can see Q plus F over P plus F over P, right? So you can see Q plus 0 over P. So F0 in modulo 2 arithmetic is our operation, right? At transmitter CRC generation, so of course we are generating CRC and multiply, right, 2 into 2 raised to the power n minus k into D, left side by n minus k bits, divide, so we will be divide by P, remainder as the frame checksum. At the receiver side, CRC checking, so divides the received T, that is T bar now, by the known divisor P, and so there should be a synchronization when we talk about the divisor between sender and receiver. There is any remainder, so then in that case there is the data is corrupted if there is some remainder. If there is no remainder or the remainder is 0, so data has been accepted, right? So given this is the data and this is the divisor, and we know that we know the methodology of calculating the divisor, so we have to find the FCS field. First, size of the data 10 bits, size of the P, right, n minus k plus 1 6 bits, hence the frame checksum length is n minus k is equal to 5. Total size of the frame is, right, so after the addition of the redundant bits, the total size of the encoded data is 15 bits, right? So here we have the solution. We have to multiply this by 2 raised to the power n minus k into D, so you can see 2 raised to the power 5 into this data bits, right? So and you can see the resultant simple shift to the left by 5 positions. So we have to use the shift register, so we have to shift left by 5, so in 5 steps. Now we will be dividing by divisor, right? So quotient, and this is the remainder. So frame check sequence, append it to the D to get the full frame to be transmitted, right? So this is the frame check sequence, right? Right, so that's all for today's, and we will resume this review and recap of the underlying chapter in our next lecture. So that's all for today's lecture. आज के लिए इतना ही काफ़ी है. अपना ख्याल रखिएगा. मेरी तरफ से अल्लाह हाफ़िज़. अस्सलाम वालेकुम.